Hello everybody, thank you for coming to our 9th lecture. Today we're going to talk about dimensionality reduction and clustering. Today's lecture is the last lecture in the series, and we're going to look at methods which allow us to reduce the dimensionality of our data, which is in some sense the inverse thing of applying the kernel, which allowed us to add more features to the data. And we're going to look at clustering, which is a way to find groups in the data. Both of the things that we want to do today are unsupervised methods. So here there are no labels that we want to predict. Instead, the machine learning methods are supposed to come up with are supposed to find some structure in the data that we have. So let's start with the dimensionality reduction. So the question, of course, at first is why should we even want to reduce the dimensionality of our data? And we already mentioned it when we were talking about the kernel, or especially the neural networks. Sometimes it is not really helpful to have all kinds of features, and it is not helpful when they are not really related to the problem. And this is actually quite often the case. So and when you get real-life data, maybe about a customer, you might have information about him that has nothing to do with the specific product in mind. So when you, for example, know about the shoe size, it will have very little predictive effect on whether or not the customer is going to buy a car. So in this sense, it will often be the case that you know a lot of things, but they are either not useful to the problem at hand, or they are kind of the same thing. That can happen as well. So when when you have knowledge about a person's shoe size and you have knowledge about a person's height, chances are that on average the two are kind of the same thing, but in a different scale. So when you have a human being that is, let's say, 30% taller, in general, the feet will be also 30% longer. So it's kind of the same thing, and you could get rid of one of them. Another problem that we have is the so-called curse of dimensionality. What is the curse of dimensionality? So since our third lecture, we know that doing anything that that has something to do with classification or with really understanding the data basically means knowing the distribution of the data, knowing the density of the distribution of the data. Now, there's one problem. When you have more and more dimensions, the input space that you need to know things about gets bigger and bigger. So to illustrate that, if you have, let's say, 5 or 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 possible values for your data in one dimension, and you have 10 different data points, you will have sampled the whole space. You know everything. You have seen all of it. But what happens if we add another dimension? With again 10 possible values. Now our 10 data points actually only sample 10% of the total space. Now let's add another dimension, we're down to 1%. Add another, we're down to 0.1%, and so on. So if you have 5 features already, your 10 data points don't tell you anything anymore. And the more dimensions we have, the more opportunities or combinations we can also find. So it becomes easier and easier now to overfit. So when we have a complicated model in high dimensions, it will certainly be able to find a very good fit. Another problem is, but that fit is meaningless. Another problem is that in high dimensions, the usual metrics, the usual norms that we use to measure distance become kind of meaningless actually. So you will find that pretty much everything is very far away from each other. And that makes a big problem when you want to use something like nearest neighbor classifiers. So the way to combat that now is to do basically the inverse of a kernel mapping and get rid of features, or better, map our input data into some lower dimensional space. So what is a PCA? PCA stands for Principal Component Analysis. There are many different interpretations of that, which all do the same thing. So there's a singular value decomposition, the principal component analysis, several statistic methods which all do the same thing, or methods coming from a statistics background which all do the same thing. So what we have here is we expect or we assume that our data is centered, which we can do. We can just subtract the mean. And then we want to approximate the data in k dimensions, which k is less than the number of dimensions we had originally. And we demand that the new coordinate axes are uncorrelated. So we're looking for a lower dimensional linear subspace, and we want to project on it. So we want the linear mapping, taking our data and projecting it onto the subspace. And what we demand is the approximation error in L2 with the L2 norm, so the squared length of the error should be minimal. And we want the new axis to be uncorrelated. So with that, we want to get rid of this problem here, that some of them might be the same, might measure the same thing. So let's illustrate that geometrically. We might have a few data points here, and we want to find at first just a one-dimensional subspace with which we can approximate the data in the best possible way. So in blue, those would be the vectors of our data. It might be x1, x2, x3. And here with green, I can draw in the error that we have here, the information that we lose because we project it. Now, can we somehow calculate the error? And our linear subspace that we project on is the span of U. So without loss of generality, we can assume that the length of U is normalized to 1. Okay, so maybe we can derive a formula for epsilon 1 for our first error. So what we can see here is that we can draw in a triangle here, and we can apply the Pythagorean theorem. Our hypotenuse here, the length of x1, is equal to the length of the projection onto the subspace U, which will be, because U is normalized, the scalar product of U with xi, but we have to square it, plus the squared length of the error. So the total error then over all the data points that we have is given by this formula. So we just rearranged here and made the sum over all data points. That means if you want to minimize this term, is the same thing as maximizing this term. Subject to the constraint that the length of U is equal to 1. And this, in turn, here, the sum can be written with a matrix vector product. Like this. So how can we rewrite that? We can rewrite it like this. Now, we have to think back to our first lecture, because again, we have a matrix, that matrix of a form that we encountered so many times before. This is a normal matrix. It's symmetric, it's normal. So therefore, we can apply the spectral theorem, and we know that there's a basis, an orthogonal basis of eigenvectors of x times x transpose. And if we want to maximize this quantity, then we have to choose u to be the largest, to be an eigenvector of the largest eigenvalue of x times x transpose. So I added an index 1 because later on we want to not just protect on one-dimensional subspace, but we might want to add more dimensions. So with this we can index. So choose u1 as an eigenvector to the largest eigenvalue of x times x transpose. Now with that, we can get the first new dimension. So the first axis, first coordinate axis in our new reduced dimensional coordinate system will be the projection of our data on that u that we just found. So a data point x is mapped to u1 transpose x, and the whole data set therefore the same way, and we can transform it now. We can project out the first axis that we have found. So our data first looked like that. And we found this as the first axis that we want to project on. And we can now take out that component, and we're left with a transformed data set here on this axis. So getting this projected data set here can be done by doing this calculation, by subtracting the component of U1. So now we have reduced the dimensionality of our data by one dimension. And we can repeat the process now. And it can be easily shown that all the components that we find this way will be eigenvectors to the largest to the k largest eigenvalues of x times x transpose. One can further show that this greedy procedure will actually give you the best approximation in terms of the L2 error. And we also know from the spectral theorem that the two consecutive directions that we choose, or any two directions that we actually chose, will be orthogonal, therefore having zero covariance. And our transformed data set, or the coordinates in our new data, the representation of our data set in the new coordinate system can be then acquired by just calculating the projections of each data point onto all the new axes. So note that this here is a matrix that is k high. So before x was number of dimensions high, n high, and now after applying this transformation, we're down to k dimensions. And if we just had picked the first axis here, the data set would have been transformed to the projection of each data point onto U, just the length of the projection onto U. So from 2D we would go to 1D. And if we live in, or if the data lives in an n-dimensional, in the Rn, then at maximally we can, meaningfully, we can calculate only n components. So if we calculate all the n components, then we will have perfect reconstruction error. And it turns out that the eigenvalues here of x transpose x of x times x transpose are actually telling you how much of how big the error will be, or better, how big the variance, the yet to be explained variance in your data set will be. So by looking at the eigenvalues of x times x transpose, we can find out how highly, how many of how many dimensions the data is. At least if it's if the data has this linear structure, that it is on a linear subspace. So what we would see here, maybe for this data set, would be that the eigenvalues of x times x transpose might be something in the order of 1, and the second component might only be 100th. So if it was indeed perfectly one-dimensional, then the second eigenvalue would be 0. You call the eigenvalues of x times x transpose the singular values of x of your data matrix. And it holds that the square root of the eigenvalues of x times x transpose are the so-called singular values. And one can show that the remaining error, that the error between the projection on the lower dimensional space and this here and the original data is the squared sum of the still missing eigenvalues. So this means you can exactly choose how much of the variance you want to you want to capture and how much you want to kick out. So if you use a Python library that does the principal component analysis for you, you might have to set a parameter where you specify the percentage of the variance that you want to keep, and you might say, I want to keep 95% of the variance, and that means that of the total, this year for the matrix, it's the Frobenius norm, that the total error, I'm sorry, and that means that of the total, the sum of the squared lengths of your data, which is the variance, of that you will keep 95%. And tiny things, tiny errors, so or tiny components of that, like this direction here, which contribute maybe only 100, will be kicked out then. So there's an interesting thing to note here. So because the axes that we choose are actually eigenvectors of x times x transpose, we again can see that they will be a linear combination of our data points again. So this means we can kernelize the principal component analysis, and we can apply a kernel method on it. So to emphasize that, normally a PCA will only capture the correct dimensionality reduction, or will only perform the dimensionality reduction correctly if the data that you have is actually on a linear subspace. If it is something like a curve, then it won't work just by itself. Because a curve, well, cannot be described as a linear subspace. However, when you use the kernel PCA, you might very well be able to capture such a relationship in the data. And yeah, in your homework, you can actually try that and see how the transformation works, how it works for linear PCA, and how it works for the kernelized version, and how it behaves in both the linear and the non-linear case. So, because the optimization problem is convex, we just have to do the eigenvector computation. We have guarantees on the quality of the approximation. And by choosing an appropriate kernel, we have hopes to uncover nonlinear relationships too. And I want to give you one illustration now, how that might work. So when we have a linear data set, so it's not perfectly on a linear subspace, but fair enough. Then by just keeping one component, we transform it into a one-dimensional data set that basically looks how far or where on this line the data is. So if we had a nonlinear relationship, then that can be transformed of a kernel mapping and a PCA. Maybe also into one-dimensional representation. Where the circles might lie further to the left than the crosses. So again, we have the choice of applying a linear method with the cost of either being restricted to linear features or being forced to employ a kernel mapping with the benefits and the drawbacks of the kernel mappings. So this is how PCA works in general. We solve an eigenvalue problem, and with that we can determine the main axes via a linear transformation. We can make that pseudo nonlinear by mapping the data again into a feature space, implicitly maybe with a kernel. And in the kernel space, in the feature space, we can then do the linear transformation. So in our original space, it might look nonlinear. Another approach, but we keep, and that is the important thing, we keep all the benefits from the linear method. Another approach that we can do is to use an autoencoder An autoencoder is a neural network that tries to learn the identity function on the data X. So if n is the output of our neural network, we want that n of x is x again. But we introduce a bottleneck in the neural network that is of low dimension and that forces the neural network to first map into this low dimensional bottleneck, and from the representation in the low dimensional bottleneck, reconstruct the original input. So we then can use the activation of the neurons in the bottleneck as the new coordinates. So the architecture, the topology could look like this. We have 4 input dimensions, a bottleneck that just has 2 neurons, and then again at the end 4 output dimensions. And we want to map every input that we get back to what we had, but it first has to go through here. And here we know that the embedding cannot have more than 2 dimensions. So we know that we have an embedding here. What we then would do to transform it, we take a data point, feed it through the network, and we just grab the activation here of those 2 neurons, and those are the new coordinates. Conversely, when we have an embedding, we can get back the representation in our original space by just using this representation as the output of those 2 neurons and feeding it into the rest of the network. So again, there are some tricks, like one can reuse the weights. One can couple the weights that were used here with the weights that were used here. And it has all the benefits, but also all the disadvantages of common neural networks. Other methods so this much for the autoencoder. Other methods that I want to mention for dimensionality reduction. are random projections that use Johnson-Lindenstrauss embeddings, which allow you basically by generating a special kind of random matrix to transform your data, project your data into a lower dimensional, linearly project your data in a lower dimensional subspace with a guarantee on the preservation of distances. So the random projection will keep the distances from your original space. So every method that only relies then, so at least up to some error that is specified. So every method that only relies on distances, like RBF kernel methods, like nearest neighbors, and so on, will then be able to operate in a lower dimensional space. And they are theoretically very interesting. They tell you a lot, actually. They tell you a lot about how high-dimensional spaces behave and how projections and angles in higher dimensions usually will behave on average. So be careful. Your dimensionality reduction techniques will operate on the entirety of the data, and they will try to capture, normally, they will try to capture the data as a whole as well as possible while reducing the dimensionality. But if you have a specific problem in mind and you use the dimensionality reduction as something of a pre-processing step, then what you might end up with is that you remove the things that are actually important for your specific problem at hand. So when you use your PCA, when you use the PCA as a pre-processing step for a linear regression model, because you know that many of the features might be highly correlated and so on, and that can, as we've seen, this will degrade the condition of the matrix that we have to invert for the linear regression, and you want a better result, therefore you apply the PCA. But it might turn out that this low variance feature was actually the predictive one, and then the PCA might have kicked it out. So this is something that you have to keep in mind when you apply these methods. So now, there are, of course, as I said, many more methods that perform dimensionality reduction, also methods that are just specializing on visualization, like TSNE, and really interesting things. However, we don't really have the time for them. So now that you have the general idea, it can be a really interesting thing to just look at something, a Python library like sklearn, and look at the documentation and look at all the methods that they provide you with. And now, after attending the lecture this far, you should be able to actually understand for most of the things what is going on. You should be able to understand by now. You will be able to understand by now how what the formulae mean and what they are talking about on their website. And with that, you can get a better idea of this entirety of this plethora of machine learning methods that we all have now at our fingertips, pre-made in a very good fashion by other people, and we can, if we know how to, and if we know when to, and if we know what to watch out for, easily employ them in our projects. So let's go on to clustering, our last topic. So the goal of clustering is to find groups in the data without human supervision. So normally, in the supervised task, things that we were looking at in the past, it was the case that we already knew that this is a dog, this is a chair, and we taught the machine learning to then classify new objects into the categories that we've given. And for those unsupervised tasks, we don't know the categories. So we want the machine learning to come up with concepts like chair or a concept like dog and group the data in a way that it captures interesting relationships in between. So normally this relies on a notion of distance. So because what do you actually know then in the setup about your data? You know very little, right? The machine learning can know very little. So you have to keep in mind that the machine learning then has to fall back to, if we restrict it a lot, then the machine learning necessarily has to fall back to very general things, and distances are such a thing. So most clustering methods will find groups of data points which are somehow, to some sense, close to each other. So even if you might now alleviate the problem a little bit by applying reasonable feature mapping before, like the dimensionality reduction or anything. But in the end, it will come down to the same notion. So things get grouped together because they are somehow similar, and similarity is pretty much exactly a distance, or the distance is pretty much exactly similarity. Okay, so as this relies on the notion of distance, it becomes hard. In high dimensional spaces. And the algorithm that we're going to look at, it's one algorithm among many, many, is the so-called k-means clustering. And the idea here is that if our data is separated in some kind of groups, so there's a blob of data over here, there's a blob of data down here, then we somehow want to find the centers, the means of those blobs. And the way we do that is iteratively. We change the means and we change which data point belongs to which cluster. So now, how are we going to do that? At first, we pick our initial cluster centers as some random data point. Then we look which data points are the closest to which center. We assign them to this center. And then we set the centers into the middle, to the mean of their respective set of data points. And as long as there's a change then in the means, we repeat the process. So it might look something like this. So here we have initialized. Those are our first two samples that we picked, and now we have to look which one is closest and to which, and I'd say the boundary might be somewhere like this. So now in the first step, everything that is closer to this one than to this belongs now in group blue. The rest belongs here. Now we will update our centers. So blue will maybe go over here. Green might go over here. And from there, we repeat the process. And look which ones are closer to which. This is now very easy. And we update our centers again. And now, in the next iteration, the sets of data points corresponding to each cluster won't have changed anymore. So there's just one more, there's no change in the computation anymore, and we're done. So we will have identified those two clusters. And if we had to classify now a new data point, we would need to look if to which cluster it is the closest. So our decision boundary would be here, and if it falls here, it belongs to green. So you could have done this, of course, with not just 2, but with 10 centers for the clusters. And it would basically work the same way. The decision boundary then gets this splinter-like look, and it will, it's something that we call a tessellation of the input space. Basically, it's a bunch of linearly bounded shapes that make up each cluster. So the benefits of that is that it is very easy to implement and fast. But the drawback is that it is highly dependent on the starting values. Now, of course, this example here is very benign, but as soon as there's an overlap between the clusters, things get very messy. And all of a sudden, you can have many, many different solutions in local optima. You don't know if it's the globally best solution. And there's one thing now that I still want to talk about, or that I want to mention. So we said as long as we have a distance, we can perform nearest neighbors, and we perform k-means. We can perform k-means. So one might ask, do we have a distance in feature space? And indeed we do. So we can look at the norm of the difference of two feature mappings, and we can calculate that just the same way as we would do without the feature mapping. And as we can see here, we could write that with a kernel. So we can kernelize these kinds of methods as well. Okay, is there anything to add? Oh yes. So a thing very closely related are the Gaussian mixture models that we were talking about in the density estimation part. Basically, you can imagine each of the clusters here as, or you could interpret them as a Gaussian distribution as well. And then you not just have a classification into different Gaussian distributions, but also what you immediately get is a generative model of your data, with which you could generate new data samples. And often the starting values for Gaussian mixture model in the algorithm is determined by first running a k-means on the data. So there are many interesting things that we did not have the time to talk about, right, in our lecture. So alone for neural networks, there's so many interesting things to know. For kernel methods, there's so many interesting things to know. For dimensionality reduction, maybe some of you know Netflix or know the recommendation algorithm in Netflix, and that there was a huge challenge with $1 million prize. And they're a very clever way of performing dimensionality reduction via matrix factorization. And data completion via matrix factorization was employed there as part of the solution. And it's extremely interesting. Now, maybe some of you were a little bit disappointed that we did not go into all the crazy fancy stuff. But it is my conviction that it is more important to really understand what we're doing. And depending on where we start, it might be a good idea to first stick with things that we can understand in their entirety, right? Also, even though things like generative adversarial neural networks are very fancy and can do amazing things, the question is also, when can you actually employ them, right? So even though it is very interesting, for many applications that you might have to do in the industry, something that is a little bit simpler will do very well, or will even perform better, because you do not have enough data. There might not even be such a crazy structure that you could even employ a deep neural network meaningfully. It really depends. What you have to use really depends on the data you have at hand. So it might be that you really need that ultra low bias, and something like a kernelized support vector machine or kernelized logistic regression does not do the trick anymore. Then you can do neural networks, and there are so many libraries that help you with that give you good ideas, so many blocks that give you a good understanding of that. But otherwise, you can do a lot with the simple methods as well. And the simple methods have the benefit that we can understand them in their entirety. You can explain to people what this machine learning solution actually means. If you try that with a neural network, it will become very difficult. So sometimes for pictures, there's this interpretation, there's a real meaning with the edges, but there are many features which are not human readable at all. Like we have no clue why the neural network actually uses them. There are also very interesting questions then regarding adversarial inputs, for example, where somebody tries to cheat a machine learning method. So there's a huge variety, and the goal of this lecture was to enable you to start your journey in a way that you're not left behind by the things you see. So I hope now that after attending everything, and hopefully after doing all the homework, when you now encounter a new machine learning technique, you have the tools to understand what is going on, and you have a good stepping stone in your career. So thank you very much for taking the time to attend all the lectures, and I wish you all the best for your journey. Bye-bye.